Hello to our friends joining us via recording. Today we are wrapping up lesson number 13 about the special senses. So our first part of the special senses lecture was all about the process of vision. To help us review what we talked about in that session, as well as to help us get ready for the exam, the lab exam, we're going to review some of the anatomy of the eyeball. So we started in groups as usual. This was the first thing we did with our groups. I've identified 4 of the structures that we talked about during our class yesterday related to vision. Let's go through and name them and talk about what it is that they do. So we're going to start here in the very front of the eye. This is the part of your eye that you see when you look in the mirror, or you can touch it if you've got contacts. What is this clear part in the front of the eye called up here? Yeah, exactly. This part up here is called the cornea. This is the cornea. Talk about the cornea. What were some of the ideas that you all came up with as to what the cornea does? Yeah, so biggest function of the cornea, we'll start with the fact that that bends light, or it helps us to focus. Yeah, the other thing that I would say too when we're talking about the cornea, it's not maybe a technical function of what it does, but I'm going to put here in quotes as well that this is kind of it protects the eyeball in a way. This is a really thick layer of connective tissue on the outside of the eyeball. When we start talking about things, especially like the retina as a whole back here, you really want to make sure that we don't damage that nervous tissue. So is a really thick connective tissue layer. Yeah, if you remember, Kaylin's mentioning that we've got pain receptors coming from here. When we talked about reflexes, remember our other chapter from this unit, number 4, was about reflexes. The blinking reflex is one that actually collects sensory information from the cornea here. So the cornea is sensitive. For us, we were talking about the touch sensation, right? How it makes you blink. We can detect pain though as well. We can detect a lot of different things here on the cornea, the outside part of the eye. Again though, like we started with, the biggest thing that the cornea does is it's my first way to bend light waves, to make sure they're going to make it here into my pupil and not just bounce off my iris. Then I wouldn't be able to see them. Right behind the iris, we've got some structures. They're actually on both sides here. What are these things that I find here kind of right behind the iris? Yeah, so these things here are called the ciliary muscles, or sometimes they're called the ciliary body. It's the same thing. So the ciliary muscles or the ciliary body, when we look at them, you can make a prediction about their function based on these little fibers that they have coming down here. These little fibers are actually attaching them to another structure. What structure is the ciliary muscles attached to? What's this thing here? We'll go ahead and label it while we're at it. Yeah, exactly. So this down here is the lens. The lens. So when we talk about the ciliary muscles that are attached to the lens, what is their function? They're attached to the lens. What are they doing? Yeah, exactly. The ciliary muscles are attached to that lens and they're pulling on it. So we're changing the shape of the lens. That's my function of the ciliary muscles. Remember that when the ciliary muscles contract, when these things contract, they actually decrease the size of. So I'm going to do a little drawing for us here. When we talk about our ciliary muscles, this is my ciliary muscle size relaxed. Spell. Let's assume that when the muscles are relaxed, they go all the way around the lens. So the lens would be here in the middle. When they're relaxed, they have an opening about this way. When I contract the ciliary muscles, they get much smaller. The opening in the middle gets smaller. I mention that because when we think about the ciliary muscles, remember that we said that when they're relaxed, our lens in the middle is kind of what we called long and lean, right? When those muscles are relaxed. When the muscles are contracted, my lens is still the same size, but now it's squeezing in a really tiny hole. Remember that when the ciliary muscles contract, that was the shape that I told you was short and stout, like the little teapot, right? So when my ciliary muscles are contracted, when they're smaller, I still have the same size lens, but I've got to squeeze it down small because there's not as much space when I contract those muscles. So the ciliary muscles, they can contract. They do that when we're looking at something up close. The ciliary muscles relax when we're looking at something far away. So both of them, or well, both of these times when we're changing contracted or relaxed, it has to do with helping us to focus our light. When we talk about the lens is my other structure that bends light, right? So when we're talking about the function of the lens, we could say that its function is also to bend light, but maybe, as I think somebody had put in the chat for me already too, it's all about focusing light on the retina. The lens is really what makes sure that that light gets to the retina. Because remember, our one thing that we absolutely had to learn yesterday is that light has to end up on the retina. The retina, we cannot perceive it. So my lens is what makes sure that that light gets all the way to the retina. My ciliary body or my ciliary muscles change the shape of the lens to help it to do that. Yeah, Elapina actually made a good point. The eye is like a microscope. Absolutely. How we have to focus things correctly. My ciliary muscles are kind of like my adjustment knobs, right? So they change it to focus things. I love that. That's a great thing to think about. Okay, so this whole layer here in the back is my layer called the retina, right? And in the part of the retina, we have an indentation. So this part of the retina is the part of the retina where light is normally going to focus. It's where we see really clearly. Do we remember the name of this part of the retina? Yeah, so this part of the retina, and I mentioned this to one of my groups, this part of the retina is called the Macula Ludia. The Macula Ludia. This second word, ludia, we want to make sure that we keep that in mind, when we're talking about the eye, because when we talk about balance today, we're actually going to talk about a structure that's just called the macula. So macula ludia is the part of the retina where light naturally focuses. This is where we see the most clearly. So the macula ludia, I'm going to say where we see the most clearly. Where we see the most clearly, because this is where that light is all ending up on the retina. Hey, I didn't have you label this structure, but what's this right here? Can we tell what this is right here? Yeah, exactly. So we'll add a label for ourselves here. This is the part of the eyeball called the optic disc. The optic disc. We know that because this is the place where the optic nerve attaches to the eyeball. And like somebody mentioned in the chat, the optic disc is the blind spot of the eye. Because this is where all of the neurons are leaving the retina, it's the part of your eye where you can't see. So this is the blind spot in the eye. I know one of my groups was talking about how you can actually test your blind spot and realize that there is a place in your vision that you don't technically collect information, but it kind of is, it goes to show you how cool your brain is, because when you're looking around you normally, you don't notice your blind spot. Your mind is really good at filling in the blanks, if you will. So there's a space in your vision you can't it, but your brain can predict what should be there. So we don't actually, in normal circumstances, we don't notice our blind spot, but we do in fact have have the blind spot, that spot called the optic disc, the blind spot. So some of those structures of the eye, make sure to refresh these on the models as well. And I believe probably some of these show up on the visible body review assignments too that are due tomorrow. So check out these eyeball structures. The other thing we talked about yesterday is what happens when vision goes wrong. So there were 4 different vision disorders that we talked about during class yesterday. Let's go through, as we're starting with what's wrong with these, let's go through and essentially say what a normal person might call each of these things, or how a normal person might describe it. And we'll tie that into our anatomy, because a lot of times those things go together. The anatomy problem and what a person would experience. So let's start with my first column here, hyperopia. When you talk about hyperopia, if someone has hyperopia, what can they see? Or we could say, what can't they see? If you've got hyperopia, what's going on with your vision? Yeah, so you are what we would call farsighted. Farsighted, which means that far away is clear and up close is blurry. Up close is blurry. That's my easy person description of it, right? So hyperopia, I can see things that are far away. I can't see things that are up close. Why is it? What's wrong leading me to not be able to see things that are close to me? What's the anatomy problem going on here? Yeah, so when we talk about hyperopia, remember in our groups, or our big picture, we grouped stuff together yesterday. This is an eyeball shaped problem. Hyperopia is an eyeball shaped problem. So the eyeball is really short. It's not as long as it should be. Since the short, light is focused behind the retina. Light is focused behind the retina because the eyeball is too short. So my anatomy issue is my eyeball is shaped wrong. In particular, my eyeball is too short. When that happens, I'm not focusing my light on the retina, I'm setting it behind the retina. It's not going to work for me. Now, we didn't talk a lot about this yesterday, but with this condition, hyperopia, this version of farsightedness, who can be a hyperopia? Did we do any research into that? Who can have hyperopia? Yeah, so hyperopia can be any age, any age. And in fact, if you see small children, very young children who are wearing glasses, most likely they are wearing glasses for hyperopia. Most likely they can see things far away, but they can't see things up close. So this is something that is more common in children, even more so than myopia. But hyperopia can definitely develop in any age, starting in the very young. Myopia is kind of the same way. We'll do this one a little bit backwards. Myopia is something that we could also see in any age group. When we talk about myopia, how would we describe that one? Let's start up here at the top. What would we say about what you can or can't see with myopia? Yeah, so myopia, nearsighted, which means that the stuff you can see clearly up close is clear. That's what nearsighted. I can see things that are near. Far away is blurry. Nearsighted, we see things near. Farsighted, we see things far away. Yeah, so Kaylin mentioned, and here actually let's do this. Myopia is also with the shape of the eyeball. When we talk about myopia, my eyeball isn't too short. This time, my eyeball is too long. Eyeball is too long. So because the eyeball is too long, light is in front of the retina. In myopia, light is in front of the retina. In hyperopia, we sent it behind. That's because the shape is wrong, but it's wrong in different ways. Your eyeball can be too short or it can be too long at any age in your life. It could be a child, it could be an adult. But when we talk about presbyopia, who gets presbyopia? Who's presbyopia? Yeah, exactly. Presbyopia. Here, so this is going to be, we'll put a note here, older people. So it's typically 35 and up, 5 plus. We all hope that it's much later than 35, right? Otherwise, it's starting way too early. So yeah, so Kaylin mentioned, because we should add that to our list here. I'm gonna draw a little line. When we talk about presbyopia, this is another one that is an example of farsightedness. So this is another farsighted, meaning we can see things far away, but we can't see them up close. But this is the one, remember, where we put the qualifier on it, and that it was age-related. Age-related farsightedness. Age-related farsightedness, which means that we can see things far away and not up close, which is why you see older people holding that can at the grocery store way far out, right, to look at it, or lifting up their glasses and squinting. I make these jokes because this is me. Like I said, this is going to be me in like a couple of years. I'm going to be that person. So age-related farsightedness. You can see things far away, so if we put them farther away, hey, it's the same problem as hyperopia. Presbyopia is farsightedness as well. But is presbyopia an issue with the eyeball shape? What causes presbyopia? Yeah, it's not the eyeball, right? The eyeball's just fine. Well, clarify that. The eyeball could be too long or too short from earlier in life, but with presbyopia, yeah, this is a problem with the lens and the ciliary body. The lens and the ciliary body, absolutely. So as we get older, the lens is hard and the ciliary muscles, ciliary body is weak. For us to be able to see up close, remember, like we showed on the previous slide, for us to see up close, we've got to squeeze that lens into the short and stout position. We need to use those muscles to squeeze it. If those muscles are weak and the thing they're trying to squeeze is hard, as we get older, it's just going to be harder for us to do those things. So we can't see up close because the way we do that involves these things. And like Kaylin said, it's all falling apart. We're getting old and it's all falling apart. Absolutely. All right, one last condition that we talked about yesterday, and that last condition was astigmatism. When we talk about astigmatism, what were some of the things that you said in your group? So either what's wrong or the anatomy. What did we say about astigmatism? Yeah, so astigmatism, this is an issue with the cornea. And yeah, I like the way that Kira described it. Kira just described it as blurry vision in general. I like that. Because astigmatism, it's not that up close is blurry or that far away is blurry. It's just like everything is blurry. Yeah, because the problem is the cornea is shaped wrong. Cornea is shaped wrong. And with the cornea being shaped wrong, we have multiple places that light goes. Multiple places that light goes. If the light goes to all those different places, we're not focusing it on the retina where it needs to go, and we're not going to be able to see. So astigmatism, your vision in general is just blurry because we're focusing light in more than one place. What did we find about astigmatism? Is this something that we see at age, or do we only see it in older people? Yeah, this is another one that can be any age. Anybody can have astigmatism. Anyone's cornea can be shaped wrong. It's unlike what we saw with presbyopia, where the reasons that it happened were specifically because you get older. This table, if you haven't already built it in your notes, or if you haven't already screenshotted it on your phone, take a quick picture. This is a great way for you to study and compare and contrast these things. Wink, wink, nudge, nudge. This is the kind of stuff that you want to know for the exam, because I'm promising you, I'm going to ask you questions like this, right? Ask you which two of these disorders are an issue with the eyeball shape, or which two of these disorders can we see stuff far away but not up close. So I want you to try to make connections between things that are similar and things that are different. So a good study table for you. Before we move on, any last minute questions? Or give me a thumbs up if you're feeling pretty good. All right, let's jump back in to lesson number 13 then. We are going to start with this image. Can you tell me what page we are in the packet for this image here? What page is this one on? We're frantically. This is where we first start talking about waves, or hearing, excuse me, the wavelengths. Okay, so we're looking at page 10 in the packet. So lesson 13 packet, page 10. When we talk about you hearing things, we are primarily listening for the pitch of a sound. So some things that we hear are high pitch, some things that we hear are low pitch. When you're hearing something that's really high pitched, that means the sound waves are traveling really quickly. When you're hearing something that's more low pitched, the sounds are traveling a little bit more slowly. This is different from if you're hearing something that's loud versus quiet. If we're hearing something loud, just for your reference, the sound waves are bigger. Something in physics we call their amplitude. And if you're hearing something quiet, those sound waves are a little bit smaller. In the process of hearing, what we're going to focus on today is your ability to detect things of different pitches. Now, remember, just like with vision, I am not going to, does a high-pitched sound travel fast or slow? I'm not going to ask you that. I just include this to show you, because when we talk about your ability to hear sounds, we actually hear these sounds that travel at different wavelengths, so either fast or slow. We literally hear them at different places in the cochlea. So there are special places in the cochlea that hear things that go fast, and special places that hear things that go slow. All of our hearing happens inside the cochlea, where we actually perceive it. Remember from lab that we start in the external ear. So you've got the auricle on the outside that collects those sound waves. Internal acoustic meatus, here I'll type that for us because that was our lab word for it. External acoustic meatus, that's my ear canal here on the outside. Sound waves get to the end of the external ear at the thing called the tympanic membrane, or the eardrum. The eardrum starts to vibrate with those sound waves. It's attached to the malleus, that's my first ossicle. Then the incus is next door, and the stapes is after that. Remember that the middle ear, which is this region we're looking at here, this is supposed to be air-filled. Right now, my poor son, his middle ear is not air-filled. It's filled with fluid because he's getting over an ear infection, but it's supposed to be air-filled like we see here. I apologize, I'm apparently cutting out. Have we been able to hear everything I said? Does it just come choppy? Kira says she's hearing me a little bit choppy. Okay, maybe they're working on my internet again. If you lose me completely, make sure to let me know. Okay. Sorry, I'm not sure what's up with that. Okay, so malleus to the incus to the stapes. This is what we go through in the middle ear until we hit our oval window that's hiding behind the stapes. That's how we get our sound waves from the middle ear into the inner ear, where I see the cochlea for hearing and where I see the areas called the vestibule, which has those semicircular canals, the macule and the utricle. So we will come back to the vestibule when we talk about balance. The cochlea is where we're going right now when we talk about hearing. This picture should look familiar because you had it in the lab guided lesson as well as here in lecture. When we talk about the process of hearing, sound waves are going to be perceived at different places along this tube called the cochlear duct. So remember from lab that there are 3 fluid-filled tubes inside the cochlea. The first tube where sound waves immediately go is what we call the Scala Vestibule. So the Scala Vestibule is the first fluid-filled tube that we see in the cochlea. Sound waves come in here and they bounce and bounce and bounce until they find the perfect place along the cochlear duct where they can be heard. Sound wave that's really high pitched, so you're traveling really fast, you'll go into the cochlear duct up here at the very beginning. If you're a more low pitched sound wave, you'll be perceived by the cochlear duct a little bit farther down. So remember how we looked at the picture of the sound waves. If you're going really fast, you'll get into that cochlear duct right away. If you're going more slow, you will work your way through the cochlear duct down over here. Sound waves bounce out of the Scala Vestibule into the cochlear duct, where we'll talk about how they're heard. Once you've perceived them or heard them, we send them down here into Scala tympani, and I think it was in our class we were talking about how Scala tympani is like the trash. This is where sound waves go to die, so they bounce around in Scala tympani. They bounce and bounce until they get to this round window, which is like the cousin to the oval window. The round window bounces sound waves out, but because there's no bones here to catch those sound waves dissipate. We don't hear them anymore. So, important thing for us to know, we go from Scala Vestibule into the cochlear duct into Scala tympani to get rid of those sound waves. Yeah, so Kira asked a question about how people can lose hearing of different pitch. I would suspect, Kira, that it does have to do with where in the cochlear duct you hear a sound. So that's why people may struggle more to hear the high-pitched or the low-pitched sounds, because we hear them in different places. Absolutely. I couldn't explain why. It's maybe a little bit harder to hear the high-pitched than the low-pitch, but it definitely makes sense that it would be different kinds of sound waves that are heard in different places. That we start to lose hearing some of them. Yeah, and Elapina asked about cats and dogs. cats and dogs is their cochlear duct is actually a little bit more advanced than ours, or a little bit longer than ours. So the range of sounds that they can hear, some of the stuff they're hearing is outside of our range. So I'm not going to ask you about this, but I'll mention there's this little area over here. This little area over here is called the Helicotrima. So the Helicotrima is a place where the Scala Vestibule actually connects directly to scala tympani. So there are sounds all around you all the time that you can't hear. That's because they bounce all the way down this cochlear duct and there was nowhere that they could be perceived. So if I can't hear them, I'll actually just send them straight through this roundabout right here, the Helicotrima. They'll go straight from the first tube straight into the trash. I'm never going to hear them. In cats and dogs, other animals, some of those sound waves that in the human ear go straight into the trash, animals can actually perceive them. So their cochlear duct hears things a little bit differently than ours, or can hear more than ours. Their range is different than ours. How do we feel about the process of hearing? Thumbs up, thumbs down. Hopefully it's mostly review from lab. Kaylin mentioned issues with the order that things go in. Yeah, just keep practicing that one would be my recommendation. The other thing too, if you're a hands-on learner, is you could actually make some flashcards that have the names of these structures on them, mix them all up in a pile, and see if you can put them in order. It's kind of like how with the process of muscle contraction, we make that flow chart, right? So if you write the name of all of these structures down on note cards, you can practice putting them in order when they're all mixed up with each other. So consider giving that a chance to see if that helps you out with the studying. Yes, so Kaylin says she has been having trouble getting them correct in the guided activity. Yeah, if you are certain that you have it right, let me know. There could be a typo in the guided activity. I haven't checked it recently, so if you're pretty confident in what order you put them in, let me know, and I can check that out for you to make sure they're not wrong. Here's some pictures that, again, should look very familiar from lab. Remember that sound waves first come into this tube called Scala Vestibule. When we found the cochlear duct that those sound waves could be heard, they bounce around here in the cochlear duct. Remember from lab that when I start bouncing sound waves in the cochlear duct, that makes this thing down here called the basilar membrane, the basement of the cochlear duct. This starts to bounce up and down, bouncing, bouncing. When this starts to bounce up and down, here's my little zoom in. We'll zoom in right here. My basilar membrane bouncing up and down. When that happens, these hair cells that are sitting on top of it bump into my membrane called the tectorial membrane. The tectorial membrane, remember in lab I kind of called it a tent. So this is my tent that's over the hair cells. They bump into it, and when they bump into it, that's how we perceive sounds. I want you, if you haven't already, I want you to underline, highlight, star the fact that these are called hair cells. We should know that from lab, but I want to make sure for lecture too that we underline, highlight, star the fact that these are called hair cells. Because every special sense we're talking about today, balance, taste, smell, all of those use hair cells. Hair cells get their name because they literally have hairs. So you can see those little hairs on the top of these hair cells. This is the part of the hair cells that actually touches the tectorial membrane. So when these hair cells get bouncing, because the sound waves are bouncing their membrane up and down, those hairs will touch and bump into the tectorial membrane. And when they bump into the tectorial membrane, the channels that are found on them are going to open up. Hey, here's another important idea for us to note on our picture here. Go ahead and underline, highlight, star that the cochlear duct, which is the place where we do hearing, the cochlear duct is filled with endolymph fluid. It's filled with endolymph fluid. Endolymph fluid, the reason why we care about that is because endolymph fluid has lots of potassium. Lots of potassium. Endolymph fluid, tons and tons and tons of potassium. If you remember way back from Unit 1, when we were talking about when we first talked about our salty bananas, right? Most of the cells in your body, there's more potassium inside them than outside them. That is not the case when we're talking about things that live in endolymph. Endolymph is a special kind of fluid in your body that has so much potassium, we'll see here in a moment, that instead of depolarizing our membrane with sodium, instead of making our membrane charge go up using sodium, we actually use that potassium to make the charge go up. So endolymph fluid is a special kind of fluid that I find in the cochlear duct, the place where I actually hear sound. Endolymph fluid, lots of potassium in it. And that's what I find surrounding these hair cells that live inside the cochlear duct. So let's look at the way that hair cells work. So here's my hair cell. Here's the cell itself. Here are all of its little hairs. You can see its little hairs up here. Talk about hair cells. They have those on their top that are covered in mechanically gated potassium channels. Oh my goodness. Unit number 1, back to haunt us. Mechanically gated potassium channels. When we say mechanically gated, how do I get those channels open? If it is mechanically gated. Yeah, exactly. Mechanically gated means I have to push these open. Mechanically gated channels are channels that I push open. What's pushing open the mechanically gated channels on my hair cells is that thing called the tectorial membrane. The tectorial membrane. Remember, this was the tent. So the tent is on top of my hair cells. When these cells start bouncing, because the place they're sitting on is bouncing up and down, these hairs bump into the tectorial membrane, and that literally pushes open mechanically gated potassium channels. In comes potassium, and look, that potassium depolarizes my membrane. When we use this word depolarize, what does that mean about my membrane charge? If I depolarize, do you remember what that means? That's a neuron word for us. Yeah, exactly. So when I depolarize my membrane, membrane charge goes up. Membrane charge goes up. This is where, remember I told you, these cells are a little bit different than our normal cells. Most cells, we would use sodium to depolarize. In these cells, because there's so much potassium outside, potassium is what I'm going to use to depolarize these cells. Potassium is a cation, just like sodium. So potassium has a positive charge, just like sodium does. Since there's so much potassium out here, that's what I'm going to use to depolarize my membrane. When I bring in my potassium and I depolarize my membrane. I make my membrane charge go up. The reason I do that is channels right here. These channels right here are voltage gated calcium channels. Voltage gated calcium channels. What does voltage gated mean? If something is voltage gated, how do I get those ones open? Voltage gated. Yeah, exactly. It's all about the voltage, right? So this is a change in charge. A change in charge. Hey, voltage gated calcium channels bring calcium into my hair cells. They open when the hair cell is depolarized. We talked about voltage gated calcium channels in neurons as well. Does anyone happen to remember where on a neuron did we have voltage gated calcium channels? Yeah, exactly. Elapina mentioned. Here, it's been a little while since I've drawn a neuron. I feel like I need to draw one for us. Our friendly reminder that the one place on our neuron that we had those voltage-gated calcium channels was down here at the bottom. This is where we had voltage-gated calcium. You didn't get to see that typo, but the word voltage had like 4 O's in it. That was pretty exciting. Voltage-gated calcium channels. The only place I have those are down here at the axon terminals. When my voltage-gated calcium channels on neurons opened up, what was the goal? When that calcium came inside, what did that make happen on my neurons? When the voltage-gated calcium channels opened up. Yeah, exactly. This is what makes my neurons talk, right? So when voltage-gated calcium channels opened on neurons, neurotransmitter release. Neurotransmitter release. Hey, check this out. When I'm looking at my hair cell, calcium comes inside. Calcium comes inside and neurotransmitters are released. This is just like with the neurons. When calcium comes in, these neurotransmitters are like, peace out, I'm not staying here. They leave the hair cell and they're detected by a neuron. The neuron that's going to help you that you're hearing a sound. There was a great note in the chat earlier. It was related specifically to this potassium stuff going on up here. The note said that these cells don't follow salty banana. And that's totally correct. For these cells, the solution that they live in has a ton of potassium inside that solution. I guess we could kind of say that these are bananas that are soaking in banana juice or something. I don't know. Come up with some analogy that helps you out. There's a lot of potassium on the outside, more than there is on the inside. The reason there's so much potassium is because we have this special kind of fluid called endolymph. So endolymph is a fluid that has a bunch of potassium. When I press on my mechanically gated potassium channels, in comes the potassium, which makes my membrane charge go up. I depolarize, which makes me open up voltage-gated calcium channels, which makes me spit out my neurotransmitters. This is a step-by-step way that you perceive a sound. So this picture would be a really good one for you to make sure you can describe. So explain what's happening with these channels up here and how that contributes to these channels here and how ultimately that makes me hear a sound. This is the physiology of a hair cell. So zooming in up close on a hair cell. Let's take this physiology and apply it to how you actually hear things. Can you help me out in the chat? What page is this picture on in your outline? What page now? Okay, so we're on page 13. On page 13, you can see kind of the 3 states that our cochlea can be in. So the first state that we're in, we would say that we're at rest. So at rest, if we were to describe what that means, is we're waiting to hear a sound. It's been a while, we haven't heard anything in particular. In normal circumstances, this is what it looks like with a hair cell in your ear. Right here, we see the state where our hairs are bent toward our tallest hair. This weird stereocilium word here, you can ignore it. It just means hair. So this right here, when we're bending that tallest hair, this is what happens when we're hearing something. When we're hearing something, our hair cells bend toward that really tall one. When we've finished hearing something, then we start to bend the other way. When we've just finished hearing a sound, when we're putting those sound waves into the trash scala tympani, this is what it looks like. So I'm going to put a note here, when we've just finished hearing something. So here's how the process of hearing works. You wait to hear a sound, you hear a sound, and then we get rid of those sound waves. Then we go back to waiting until we hear something, and then we get rid of those sound waves, and we go back to waiting. Everything in anatomy and physiology is a big circle, right? So when we're waiting to hear a sound, my hair cell is sitting on top of my basilar membrane. When it's sitting on top just normal, that tectorial membrane touches it a little bit. So there's a little bit of pressure. Notice over here how it says a few of the channels are open. So we've got, remember, mechanically gated channels. Just by the fact that those hairs touch the tectorial membrane, that pushes a few of those channels open. When a few of the channels are open, we send a few messages. So think about what's happening when you're waiting to hear a sound. It's kind of like when you think of a submarine that has sonar, where it sends out little pings, little messages. So a few messages are sent. When we're waiting to hear a sound, your hair cells send out a little message just to say, hey brain, I'm listening. Haven't heard anything. I'm listening. I'm listening. We send out just a few messages because a few of our mechanically gated ion channels are open. When a sound wave gets into the cochlear duct and it starts to make that basilar membrane bounce, it bounces in such a way that this hair cell completely smashes into the tectorial membrane. When that hair cell completely smashes into it, we open up all of the mechanically gated ion channels. They're all pressed open. So those channels, a whole bunch, as we open those channels, in comes that potassium. And remember, as the potassium comes in, that's going to ultimately open up those voltage-gated calcium channels too. When I bring in all of the potassium, that means I'll bring in all of the calcium, which means I'm going to spit out all of the neurotransmitters. Check out here on my nerve that's listening for messages. We are hearing all kinds of messages because we're spitting out so many neurotransmitters down here. When you're hearing a sound, lots of messages are sent. Lots of messages are sent. So your brain knows that you're hearing something when your hair cell spits out a ton of neurotransmitters. You process that in your brain as I'm hearing something. something important. But remember that once you've heard a sound, we want to recycle those noises. We want to spit them back out. So we send them into scala tympani. When we do that, see how the basilar membrane is bent the direction now? When we bend the basilar membrane this direction, we actually push our mechanically gated shut. So we close them. Now there's no potassium. Now there's no calcium. If that's the case, there are no neurotransmitters because I need calcium to spit out a neurotransmitter. I'm not going to spit out calcium unless potassium came inside. And since everything's closed, I'm not doing any of this. And you've just finished hearing a sound, the way your brain knows that we're not still hearing that pitch, there are no messages sent. No messages sent. When we're waiting to hear a sound, it's kind of like the reticular activating system. Remember that from the brain, where we said it sends out little pings. When you're waiting to hear sounds, the hair cells send out little pings and tell the brain, I'm waiting. I'm not hearing anything, but I'm waiting. When you hear something, we send a ton of messages to the brain, telling the brain we're hearing something. But when we're done hearing that sound, we completely stop sending messages. All of those ion channels gets pushed completely shut. Your brain interprets the 0 messages to mean whatever I just heard, I'm not hearing it anymore. I need to pause and give you a moment to process. How do we feel about the number of messages that we're sending in each of these situations? Okay, we're feeling pretty good. Well, you will have some practice on the homework assignment that will literally ask you in these same terms: no messages, lots of messages, or a few messages. Make sure we keep track in our mind. How many messages do I send when I'm waiting to hear a sound, when I'm acting, and after I'm done hearing something? The three conditions we can be in with sound. This idea of sending different numbers of messages to help our brain interpret what's happening, this is an idea that also, when we're talking about balance, when we're talking about equilibrium. So we just talked about this portion of my inner ear over here, the cochlea, where we send things in Scala Vestibule, then into the cochlear duct, then we get rid of them. That's how we hear. When we're talking about balance, we're going to do that in 2 different ways. Some of the balance that we're going to do is with these big fluid-filled areas called the saccule and the utricle. And we remember those from lab. This is where I'm going to balance relative to gravity. So consider when I like to joke with the saccule and the utricle. These are the parts of your ear that should help you not fall asleep in class. So when your head starts to bend forward in class, or my favorite is when someone's completely out and their head goes backwards in class, what should help you not do that is what's going on here with the saccule and the utricle. So helping us, correct me, can you remind me, what's the technical term that I use for that kind of equilibrium? Is it static equilibrium? Okay, wanted to make sure I said it correctly. There's a couple of different words you can use for it. So static equilibrium relative to gravity. forward or backwards. That's the saccule and the utricle, these parts down here. When we talk about rotational equilibrium, that's my semicircular canals that I see here. Here's a big picture idea that I want you to write down. I want you to write down that all of these labeled structures here, everything listed here, is filled with endolymph. All of these structures, the semicircular canals, the utricle, and the saccule, cochlea for that matter, because we just talked about it, all of them are filled with endolymph fluid. Now, technically, it is, here, let's qualify. Technically, it's the cochlear duct that has endolymph. Your picture shows you that those two scalas on the outside of it, they don't actually have endolymph fluid. I know there's a question on your homework assignment that asks about that. That's why I wanted to emphasize it for you. Wherever we're actually detecting balance or hearing, we have endolymph fluid there. So let's start with what's going on in the saccule and the utricle. These were the parts, if you remember, the two big fluid-filled areas that I find in this area called the vestibule. When we talk about the saccule and the utricle, what I use to detect static equilibrium, I'll add a note here, static equilibrium, I use the saccule and the utricle to do that. Now, here's why from our activity earlier, I mentioned that we have to clarify that the eye has the Macula Ludia, because the saccule and the utricle, they also have a macula. So in the saccule and the utricle, the macula is a special membrane that helps you to detect static equilibrium. The way we detect static equilibrium, so here we've zoomed in close on that thing called the macula. I really, really love static equilibrium because these things are my favorite. Dr. Allis loves her some otoliths. So otoliths are little calcium carbonate crystals. They're basically little rocks that we have inside your ear. These rocks are sitting on top of a jello-like membrane here. This membrane, we've got these otoliths on top of it. When you bend your head forward or backwards, these little rocks that sit on top of the otolithic membrane, these little rocks move. And when they move, they push open some channels on the hair cells that I find in the macula, the hair cells in the macula. Remember how I told you hair cells are everywhere? So inside these membranes, in the area called the macula of the saccule and the utricle, we've got hair cells that have otoliths, have little crystals sitting on top of them. When your head is upright, so when you are looking at your computer screen, if it's elevated for you, those otoliths sit right on top of the otolithic membrane. They sit right on top and they press down on some of the hair cells here. Notice that we send a slow and steady ping to our nerve here. So when your head is upright, I'm going to call it slow and steady. Slow and steady. The number of messages that we're sending. This is what your brain is listening for to tell you that your head is upright. Now, if you are starting to fall asleep in class, you're starting to nod forward, notice how as we nod forward, the otoliths pull forward. As the otoliths pull forward, they press a whole bunch of those mechanically gated channels. When we open up those mechanically gated channels, we also open up the voltage gated channels. Long story short, we send a ton of messages. So when your head tilts forward, we send lots of messages because we've opened up the mechanically gated channels, we're depolarizing our membrane, and that's going to make us spit out a bunch of messages. So when you tilt your head forward, you're starting to fall asleep in class, or you're driving and you're starting to fall asleep, your brain will send out a whole bunch of SOS messages because those little otoliths tilted forward and put the mechanically gated channels. If you're completely falling asleep, so your head's starting to tilt backwards, my hair cells will push, or excuse me, my otoliths will push on those hair cells once again, but this time when they push on them, they're pushing some of them closed. So when we push them closed, our head is tilting backwards. That makes us release very few messages. Very few messages. Notice how my rate slows down as we see here. So when your head goes backwards, we don't send out as many messages. Notice how it says my action potentials go down. When our head goes forward, we send out a lot of messages. Our action potentials go up. Otherwise, we've got a steady number of action potentials, or a steady number of messages that we're sending that tells us that our head is upright. We're not tilting forward. We're not tilting backwards. Yeah, so Elapina asked about this weird word, this thing called the Kenocilium. If you remember when we were talking about hearing, they had that word stereocilium. So this Kenocilium is the same idea. What Kenocilium, what it is on a hair cell, it's the tallest hair. The tallest hair on a hair cell. Tallest hair on a hair cell. That's a great question. So the Kenocilium, when we talk about bending toward it, that means we're going to push open the channels. So opens the, I'm going to abbreviate, mechanically gated channels. When we talk about that tallest hair, when we are bending away from the tallest hair, that closes the channels. Closes the channels. That's why we end up sending so few messages, because I'm pushing those things closed. So just like with hearing, there's a normal, slow and steady number of messages you should be receiving when your head's upright. If we bend forward, we send a bunch of messages. If we bend backwards, we only send a few messages. The number of messages we send has to do with those mechanically gated ion channels. My otoliths press on them and either press them open or press them closed. That's how we determine the number of messages we send. Thumbs up, thumbs down with this static equilibrium. Okay, so this is the kind of balance that we do forward and backwards relative to gravity. Let's talk about what it looks like when we're doing rotational equilibrium. So giving you an idea if your head is kind of rotating to the side, if you're spinning, all that kind of stuff. That is done in the semicircular canals. Now, remember from lab that we had a big region of each semicircular canal. I'm going to circle here. Each semicircular canal had an enlarged region, and that enlarged region on the semicircular canal, yeah, exactly, was called an ampulla. So we've got these long fluid-filled tubes. They're filled with endolymph. At the end of the fluid-filled tube, you've got this big, large space called the ampulla. And the reason I have a big, large space is because I need my membrane cupula. Hey, here's a wink, wink, nudge, nudge. And we will do this in a review session. We need to compare the terminology of what I use for each of these special senses. So for dynamic equilibrium, I have this little membrane. Again, it's kind of flexible like Jell-O. I've got this membrane called the cupula. This is going to sway backwards and help me to figure out if I'm rotating. This cupula is a lot like that macula that we were talking about on static equilibrium. So the place that had the otoliths and the otolithic membrane. You should be thinking with those words, static equilibrium. When you hear the word cupula, we should be thinking dynamic equilibrium. So the way dynamic equilibrium works is I have this large gelatinous membrane, or that's sticking up, called my cupula. Embedded in it at the bottom are hair cells. See my hair cells? And they've got their little hairs that are sticking out. Again, we're going to use some of those words that we saw before. These are just fancy words for hairs on top of the hair cells. Their hairs stick up, cupula. When we rotate, the endolymph fluid that's around this cupula will push on it. So it'll push it forwards, it'll push it backwards, depending on what kind of rotation you're doing. So the way we detect rotation is by the moving of this cupula. It sways forward and backwards. The way we detect if you are bent forward or backwards is when those little otoliths, when they move across their membrane. Movements of the cupula or movements of the otolith, it ends up doing the exact same thing. Here's those hair cells. Before you start spinning, so say you are ice skating and you're really awesome because you can spin like this. Say you go out onto the ice, you haven't started spinning yet. Your cupula is standing upright. When you are not rotating, again, this is an example of the slow, steady number of messages. A few of my mechanically gated ion channels are open. So I depolarize my membrane a little bit. I spit out a few neurotransmitters, a slow and steady number of neurotransmitters being released before I start spinning. Then I start spinning. When I start spinning, my cupula spins with me, but the fluid that's found inside of it takes a little bit of time to start moving. So when you first start spinning, the endolymph that's inside your semicircular canals, it doesn't spin with you right away. The endolymph fluid, when you first start spinning, is going to bend your cupula and make you spit out a lot of messages. See how it says it excites the hair cells? We spit out a lot of messages. That tells our brain we are spinning. When you stop spinning, your cupula stops moving, but that fluid is still moving around. Fluid kind of a bit of a lag time, and you've probably noticed this actually. If you spin a whole bunch of times and then you stop, you feel a little bit dizzy, right? Things feel weird. It's because that fluid inside your ampulla is still moving. When that fluid is still moving, that pushes the cupula the other direction. When it pushes it the other direction, it pushes the cupula, or pushes those mechanically gated channels closed, and we spit out very few messages. We inhibit our hair cells, or we close those mechanically gated channels and send fewer messages. Your brain goes from receiving a lot of messages telling us that we're spinning to receiving very few. That tells us that we stopped. And ultimately, once that fluid is done spinning incorrectly, so once it's figured out that we've stopped, you'll end up with that cupula upright again. And that will tell your brain through the slow and steady messages that we are done spinning. With the process of hearing and the process of static equilibrium and dynamic equilibrium, this is how I want you to learn these processes. Essentially, I want you to know, how many messages am I sending? A slow and steady amount, a really high amount, or a really low amount? Or in the case of hearing, I actually send none, right? So this is the way I want you to study these processes and use our discussion of those mechanically gated channels to help you as you consider why I sometimes send a lot of messages or why I don't send very many at all. Thinking about these processes, what do you think is the hardest for you as you're considering studying these? What's the thing that maybe makes the least sense or is the most? What do we think with? Kaylin's mind is just blown. It is hard to put to words. Like I mentioned, we will do a group activity to practice this. Yeah, it's just going to take some processing. Absolutely. This would be a good thing. Here's a wink, wink, nudge, nudge. This would be a really good thing. Hearing and the types of balance. Make yourself a table like we did with the vision disorders. And on that table, you could say, what's happening when I've got a slow and steady of messages? When we're talking about slow and steady in the ear, we are waiting to hear a message. When we're talking about slow and steady with static equilibrium, that means our head is upright. Or slow and steady with dynamic equilibrium, that means that we aren't spinning, we haven't been spinning. So try to outline for yourself what does it mean in dynamic equilibrium that I've got a lot of messages? Or what does it mean in hearing when I've got a lot of messages? What does it mean when I have very few or no messages? Consider trying to make yourself a practice table to review those things. Yeah, so Fanchon's mentioning it's a little bit harder with the hearing. No, I totally get that. You could always test your dynamic equilibrium by spinning a little bit and then stopping, right? That's the best way, honestly, that I feel like to visualize this step here is that weird feeling you get when you first stop spinning, that weirdness that you're about to fall over. That's because your cupula is switching directions, saying, whoa, what is happening here? We were bent one way, now we're bent the other. What is going on? Yeah. So continue to think about this. We'll absolutely talk about it more next week as we're reviewing it some more. But like I mentioned, consider making a table or consider practicing these things, right? Do a little bit of spinning, put your head down. You can say that Dr. Ollis, you need to fall asleep with your head facing forward. I'll take that one. Actually, fun story. My 10-month-old, he has this bad habit. Sometimes he will sit up in his bed like for an hour in the middle of the night, and he will sit in his bed until his static equilibrium catches him. He'll start to bend forward. His eyes are completely closed, like he's so tired. It's really funny to watch him on the baby monitor as, here, let's go back. We got this action going on. He will bend forward and then snap himself back up. Like he gets just enough messages for his brain to know that he's leaning forward, and he'll put his head back up. And then his eyes will close again and his head will start to bend forward until there's too many messages and it wakes him back up. So it's fun to watch, except at 2 in the morning. It's not so cute at 2 in the morning, but it's pretty cute at like 8 o'clock at night, watching him sit up in bed and watch him trip his static equilibrium. So static equilibrium uses those otoliths, forward and backwards. Dynamic equilibrium uses that cupula. That's when we're spinning. And then remember that we also use that tectorial membrane in the process of spinning. All of those senses use endolymph fluid. All the places in the ear where we hear or balance, we've got that special endolymph fluid. I see a note that I was cutting out. I apologize. Do we think I'm back now? Yeah, so the tectorial membrane is for hearing, cupula for balance, and then the otoliths for static equilibrium. Let's talk about our last two senses. Smell and taste are going to seem so easy. All of the other senses, I saved the best for last. So this should be really easy for us here. We are talking about the process of smell. Our next special sense is smell. And the sense of smell is olfaction. So olfaction is a sense of smell. We smell in our nose. The place in your nose that you smell is about 1 square inch. So imagine inside your head, 1 inch by 1 inch. Every single thing you smell, we detect it there. Remember that we use cranial nerve number 1 to help us with the sense of smell. So if you recall from lab, there was that place in the skull where there was a bunch of little holes, the things called the Cribriform Foramina. You can see that word right here, Cribriform Foramina. Those are little tiny holes where we actually send down nerves into your nasal cavity. So that's why we cared about those little holes. They were there for neurons to leave the olfactory nerve to go down into your nose, where we have the olfactory epithelium. Hey, so we smell using olfactory hair cells. So on here they have them labeled an olfactory sensory neuron. Let's change it to an olfactory hair cell. The reason we're changing it is, see all these little extensions? Blue was the wrong color here. These little extensions that you see down here at the bottom, these are my hairs, my olfactory hairs. And the olfactory hairs are what I actually use to smell things. So my olfactory hair cells have these little hairs that stick out. Notice that those hairs are embedded in mucus. Now, mucus is not my friend right now because Dr. Ollis has like a sinus infection, but mucus actually has an important job in you. The job of mucus is to dissolve everything that you smell. So the sense of smell is what we call a chemical sense. A chemical sense. That means two things. Thing number one that means is what we detect are chemicals. So literally what you're smelling, everything you smell, it's a combination of all the chemicals that are in that compound. But the tie-in to that is the chemicals must be dissolved. To be able to smell a chemical, I have to dissolve it in something. So that's the job of mucus, to catch the chemicals in your environment, dissolve them so that they can bump into your olfactory hair cells with their little olfactory hairs at the bottom. Hey, let's make a prediction. When we do the process of smelling, we are detecting chemicals. These things interact directly with olfactory hair cells. They open a type of channel on those cells. If the process of olfaction means I'm detecting chemicals, what kind of gated channels do you think I have on hair cells? Yeah, exactly. Olfactory hair cells have chemically gated channels. The way I open those channels is using chemicals. So the chemicals that you smell are the keys that open up the chemically gated ion channels. The chemically gated ion channels. Here's a wink, wink, nudge, nudge. When we talk about smell, we're using mechanically gated ion channels. What kind of gate did we have when we were talking about hearing and balance? What was the kind of gate that we used for hearing and balance? Do you remember the main kind on those hair cells? Exactly. Mechanically gated channels. So when you're thinking about hearing and balance, those use mechanically gated ion channels. When we're thinking about smell, and I'll preview for us, when we're thinking about taste, both of those use chemically gated channels. So that's a good compare and contrast. These are chemically gated channels on our hair cells. When someone has a cold, they make extra mucus, lots of mucus. When you have a cold, how is your sense of smell usually? Is it normal, better, or worse when you have a cold, typically? Yeah, it's not so great, right? or non-existent even. Yeah. So when you have a cold and you're making a ton of mucus, imagine that we have mucus all the way down here. So there's a ton of mucus here in the nose. What ends up happening is we still have chemicals that come in the air that we're breathing, but those chemicals get really diluted. So we have a ton of mucus. Those chemicals go in. So it's kind of like when you make lemonade from powder, right? We put 1 scoop of the lemonade into a pitcher of water, and maybe that's not so taste. We put 2 or 3 scoops in, that tastes a lot better. When I've diluted my lemonade, or when I've diluted the chemicals that I'm smelling, they're not going to bump into my olfactory hair cells as much. I'm not going to detect those smells as well. So I must have mucus. I need it to dissolve my chemicals. If I had no mucus, I couldn't detect them because they've got to be dissolved. But I've got to have the right amount of mucus. Otherwise, I'm diluting what I'm smelling, and it's not going to work. The same thing is true when we talk about taste. Taste is another chemical sense. The chemical sense of taste is called gustation. In gustation, the chemicals that we're detecting are called tastants. Tastants. And because gustation is another chemical sense, I have to dissolve the chemicals to be able to detect them. What do you think we use in the sense of taste to dissolve our chemicals? What do I dissolve tastants in? Yeah, exactly. I use saliva to dissolve my tastants. I have to dissolve them for me to be able to detect them. If I have too much saliva, I am going to dilute them away. If I don't have enough, I'm not going to dissolve them at all, and I won't be able to taste them either. Hey, the process of taste happens inside your taste buds. So this is up close and personal on a taste bud. My picture has them labeled as gustatory epithelial cells. I want you to change that to gustatory hair cells. Gustatory hair cells. That's the name of the special type of neurons that I use in the process of taste, gustatory hair cells. They're arranged together in taste buds, but taste buds are really small. So if you look at your tongue, you might see some bumps on your tongue. So along the back of your tongue, all over the top surface. These bumps that we're seeing are called papillae. Papillae are filled with taste buds. So taste buds are way smaller than these things that we're looking at. The normal bumps on your tongue, they're going to have maybe 3 to 5 taste buds inside of them. Along the back of the tongue, lots more taste buds back here. I believe the number I gave you isn't it like 50 or more? I can't remember exactly how many. It's way more than we see up here on these regular bumps, the fungiform papillae. Valate papillae on the back of your tongue, lots of taste buds. Fungiform papillae covering everywhere on your tongue, a few taste buds. These ones over here on the side are pretty cool because they're called foliate papillae. These ones over here are only seen in kids. So kids actually have some extra sets of taste buds that adults don't have. So maybe that's why kids are really picky eaters, right? Different taste buds than adults do. Or at least that's what I tell myself when my daughter won't eat her vegetables, right? It's just those foliate papillae. It's got to be the foliate papillae. When we talk about taste, here's the very last thing we'll say. When we talk about taste, you're detecting those chemicals called tastants. Everything that you taste is a combination of different chemicals. So this is things like sweet, salty, sour, acidic. We also talked about that one called umami. Umami. Umami is something that is a taste sensation that's triggered by the amino acid glutamate. So if you remember on our lecture classroom setup, I was telling you how I put Cheetos in our classroom. Cheetos and Doritos, if you read through their ingredients list, probably about halfway to 2/3 through them, they'll have that thing monosodium. Oh, I spelled that wrong. Monosodium glutamate. Monosodium glutamate. MSG. MSG registers on your tongue as umami. Umami is a taste sensation that means delicious. So if you taste umami, it makes you want to eat more of it. It makes you really happy, lights up your brain. So when you see something that has MSG in it, something like chips that have the punchline, bet you can't eat just one, this is why you can't eat just one, because it tastes delicious. It tastes like umami. So check the last part of the guided lesson. It breaks down for you the names of the other taste sensations as well and kind of how we detect them. But again, everything you taste comes down to the mixture of the chemicals that are in your food. We dissolve those chemicals in saliva, and our gustatory hair cells detect them in our saliva. Congratulations, ladies and gentlemen. That is all of Anatomy and Physiology 1. We have just finished it. Woohoo! I know. I'm excited for you. We ended on a tasty note, right? With MSG. Yeah, Gerardo asked if you should just add glutamate to everything. I bet that it would taste real good if you did. Probably would eat too much. Yeah. So with that, I'm going to call. We are absolutely going to have some review sessions next week, both for exam number 4, but also for the lecture and the lab finals. Remember, tomorrow is a lab final review session. We'll probably do another lab final review on Monday, and then we'll transition into lecture review stuff. So be watching for that schedule. I will make sure to send out some announcements. But yeah, congratulations. I am super excited for you that you have survived AMP1, or at least survived the material of AMP1. So well done.